Welcome to Lesson 1.3, How Large Language Models Are Trained. Learning Objectives. By the end of this lesson, you'll be able to explain the complete training pipeline for large language models, what happens in each phase, which phase adds which capability, what data each phase requires, and how modern reasoning models like O1 are actually built. This is the conceptual foundation everything else in this course builds on. The complete training pipeline. Models like GPT-4, Claude, and Llama don't become capable in a single training run. They go through a sequence of distinct phases, and each phase is responsible for a different kind of capability. Understanding this pipeline is what separates engineers who fine-tune effectively from those who just run scripts and hope for the best. Here's the full arc of how a model gets built. It starts with random weights, literally noise. The model knows nothing. Through pre-training, it learns to complete text, and that process gives it language understanding and world knowledge. The result is called a base model. Then supervised fine-tuning transforms that base model into something that actually follows instructions, an instruct model. After that, alignment training using techniques like DPO or PPO shapes the model's behavior around human preferences and safety. And finally, GRPO, Group Relative Policy Optimization, is what creates reasoning models that think step by step before answering. Each phase builds directly on the last. Notice the compute costs on this chart. They tell an important story. Pre-training dominates completely, running roughly 100 times the cost of everything that follows. Supervised fine-tuning comes in around 10 times the cost of the later stages. Alignment via RLHF or DPO is about 5 times, and GRPO, the reasoning phase, is roughly 2 times. The practical implication: the expensive foundation has already been laid for you. When you fine-tune, you're operating at the cheap end of this pyramid, which is exactly what makes it accessible on hardware like your P40s. To put it plainly, it all starts with a transformer initialized on random weights. At that point, the model is useless. Pure noise in, noise out. Everything interesting comes from what happens next. Walk through each phase with that in mind. Phase 1. Pre-training. Pre-training is the most expensive and foundational phase. The objective is deceptively simple. Given a sequence of text, predict the next token. That's it. But run that objective across trillions of tokens, web pages, books, code, scientific papers, on thousands of GPUs for weeks or months, and something remarkable emerges. The model develops language understanding, factual knowledge, common sense, and the ability to reason about patterns it has never explicitly been taught. The training data is completely unstructured. No labels, no questions, no answers, just raw text. The training data spans everything. A pangram testing every letter of the alphabet, a Python function computing Fibonacci numbers, a Wikipedia paragraph on artificial intelligence. The model sees all of it indiscriminately. That diversity is intentional. By predicting the next token across wildly different contexts, the model is forced to internalize the underlying structure of language itself, not just surface patterns from one domain. No questions, no answers, no instructions, just raw text. The model has no concept of being helpful yet. That comes later. Here's what the original Llama model was actually trained on. Web data from Common Crawl made up 67% of the training corpus. That's the general internet, giving the model broad language patterns and world knowledge. GitHub contributed 4.5%, which is where coding ability comes from. Wikipedia added another 4.5% of structured factual knowledge. Books accounted for 4.5%, teaching long-form reasoning and narrative structure. Receive papers made up 2.5%, and Stack Exchange contributed 2%, introducing question and answer patterns and technical problem solving. The total, approximately 1.4 trillion tokens. That's the scale we're talking. By learning to predict the next token across all that data, the model implicitly acquires a remarkable range of capabilities it was never directly taught. Grammar and syntax. Facts about the world. Paris is the capital of France. Common sense. Ice melts when heated. Code patterns and logic. Multiple languages. Basic arithmetic. And the ability to complete text in context. None of this was explicitly labeled. It all emerged from the prediction objective applied at scale. But here's the catch. After pre-training, the model is genuinely not useful as an assistant. Ask it to write a poem about dogs, and it might just continue generating text as if you wrote the opening of a blog post. Ask it what is AI, and it might generate another question rather than an answer. It has no concept of conversational turns, no sense of when to stop generating, and no filter on harmful or biased content. What you have is called a base model, extraordinarily knowledgeable, but completely untrained to be helpful. That's exactly the problem Phase 2 solves. Phase 2, Supervised Fine-Tuning, SFT. Supervised fine-tuning is where the model learns to behave. The training data is no longer raw text. It's structured examples of desired behavior, an input paired with the ideal output, instructions paired with responses, questions paired with answers, conversations with turns. The scale is dramatically smaller than pre-training, thousands to millions of examples rather than trillions of tokens, and training takes days rather than months. But the behavioral transformation is profound. This is the phase that turns a text completion engine into something that actually understands what you want from it. The simplest SFT format is an instruction output pair. The instruction field contains what the user wants. Write a poem about dogs. The output field contains the ideal response the model should learn to produce. During training, the model sees the instruction, generates a response, and the loss is computed against the target output. Over thousands of examples like this, the model learns the pattern. When someone asks me to do something, I should actually do it. The same format handles factual questions. The instruction is, what is artificial intelligence? And the output is a clear, accurate explanation. What's important here is that the model isn't just memorizing the specific answer. It's learning the general behavior of responding to questions with informative, well-structured prose. The format teaches the behavior. The content teaches the style. For conversational training, the data takes a slightly different shape. A conversations array, where each entry has a role field, either user or SN, and a content field with the actual message. This structure teaches the model something the instruction output format can't: how to maintain context across multiple turns. The model learns that a conversation has a flow, that prior messages matter, and that its role is to respond as the assistant. This is what enables multi-turn chat. The Llama 3 SFT dataset covered a wide range of task types: English question and answer pairs, coding tasks across Python, JavaScript, and other languages, STEM exam questions, creative writing, multi-step reasoning problems, and conversation examples. That breadth is what makes the resulting instruct model generalize well across domains rather than just excelling at one narrow task type. After SFT, the model is genuinely useful. It follows instructions. It answers questions with appropriate structure. It handles multi-turn conversations. It knows when to stop generating. It can refuse inappropriate requests if those refusals were included in training. The result is what gets called an instruct model or chat model, the kind of model you actually interact with when you use ChatGPT or Claude. And critically, this is the phase you'll be doing most of in this course. Phase 3, Alignment, DPO, PPO, RLHF. Alignment is about making the model's outputs match what humans actually prefer, not just what's technically correct. An SFT model might answer every question, but some answers are better than others in ways that are hard to capture with a simple correct-incorrect label. Alignment training uses preference data. For a given prompt, you have a chosen response that's preferred and a rejected response that isn't. The model learns to produce outputs more like the chosen ones and less like the rejected ones. This is how you get a model that's helpful, honest, and avoids harmful outputs. Here's a concrete example of what preference data looks like. The prompt asks for quick ways to make money. The chosen response lists legitimate options: freelance work, selling unused items, taking on extra shifts. The rejected response suggests something illegal. By training on thousands of pairs like this, the model learns not just what to say, but what kind of answer is appropriate to produce in the first place. The distinction between chosen and rejected encodes human judgment directly into the model's weights. The training signal is the gap between chosen and rejected. The model is rewarded for moving toward the chosen response and penalized for moving toward the rejected one. Over enough examples, this reshapes the model's output distribution in meaningful ways. There are three main techniques for alignment. RLHF, reinforcement learning from human feedback, is the original approach. Humans rate model outputs. Those ratings train a reward model, and then reinforcement learning optimizes the base model to score higher on that reward model. It works well but is complex to implement. DPO, direct preference optimization, is simpler. It skips the reward model entirely and trains directly on preference pairs, which makes it more stable and much easier to run. PPO, proximal policy optimization, is the classic RL algorithm used inside RLHF. Its key property is that it constrains how much the model can change in a single update, preventing catastrophic shifts in behavior. For large labs, alignment data comes from teams of human annotators rating model outputs at scale. For you, the approach is more practical. Build a simple feedback mechanism into your application, an upvote and downvote button on responses, and log the results. Each interaction where a user prefers one response over another becomes a training example. The data structure is straightforward. Store the prompt, the response that was upvoted as chosen, and the response that was downvoted as rejected. Over time, this naturally accumulates into a preference dataset you can use for DPO training. Llama 3 didn't just do one round of SFT followed by one round of DPO. The actual training pipeline looked like this. Start with the base model, run SFT, then run DPO, then run another round of SFT on the improved model, then another round of DPO, and repeat. Each iteration uses the previous model as the new starting point, and each cycle produces measurably better outputs. This iterative approach is worth remembering. If your first fine-tune isn't perfect, running another round on the improved model is a legitimate and effective strategy. After alignment, the model is production ready. Responses are more helpful and better calibrated to what users actually want. The model refuses genuinely harmful requests. It admits uncertainty rather than confident. It's more culturally sensitive and less prone to generating biased content. This is what separates a raw instruct model from something like GPT-4 or Claude. The alignment phase is doing a lot of heavy lifting that's easy to underestimate. Phase 4, GRPO, Reasoning Models. GRPO, Group Relative Policy Optimization, is the technique behind reasoning models like OpenAI's O1. It's a reinforcement learning approach, and what makes it genuinely exciting is what it doesn't require. You don't need demonstrations of reasoning. You don't need to manually write out step-by-step solutions for the model to imitate. Instead, you give the model questions and define what a good answer looks like, a reward function, and the model figures out how to reason its way to good answers on its own. The reasoning behavior emerges from the optimization process itself. The traditional SFT approach to teaching reasoning looks like this. Provide a question, what is 15% of 80, paired with a fully worked out answer that shows every calculation step. The model learns by imitating those demonstrations. This works, but it requires someone to write all those step-by-step solutions, which is expensive and limits you to reasoning patterns you can already demonstrate. With GRPO, the training data is just questions and answers, no reasoning demonstrations. What you define instead is a reward function. This one scores model outputs on 3 criteria. Correctness gets the highest reward. The presence of reasoning indicators like the words step or because gets a smaller bonus, and the use of special reasoning tokens like the think tag gets another bonus. The model generates candidate responses, scores them against this function, and updates its weights to produce higher scoring outputs. Over many iterations, it learns that showing its work leads to better scores, so it starts showing its work. The implications here are significant. You don't need to manually write reasoning examples. The model discovers its own strategies. It can develop reasoning approaches you wouldn't have thought to demonstrate. And it works for any domain where you can define a verifiable reward. Does the code run? Is the math answer correct? Does the output match the expected format? The model learns to reason in order to satisfy the reward signal, not because it was shown how. The domains where GRPO works best are ones with clear, verifiable correctness. Math problems, coding tasks where you can execute the output, factual science questions, logic puzzles. The harder cases are subjective domains, creative writing, open-ended questions, topics where good is genuinely in the eye of the beholder. But even there, creative reward functions can make progress. If you can define what you're optimizing for, GRPO gives you a path to get there. Here's what a minimal GRPO training setup looks like in code. The dataset contains math questions and their correct answers. The reward function, math reward, evaluates model outputs on 3 dimensions: correctness relative to the known answer, solution completeness, and the presence of reasoning in the response. The GRPO trainer from the Trier library takes the model, the reward function, and the dataset. When training runs, you'll see loss metrics and reward scores in the output. Watch the reward scores. They should trend upward as the model learns to produce higher quality, better reasoned responses. The model learns to show its work because showing its work is what earns reward. That's the elegant core of the whole approach. You don't teach reasoning directly, you incentivize it. Training pipeline summary. Here's the complete picture in one place. Pre-training takes random weights and produces a base model trained on roughly 1 trillion tokens of unstructured text. SFT takes that base model and produces an instruct model trained on anywhere from 100,000 to 1 million instruction response pairs. Alignment takes the instruct model and produces a safe preference aligned model trained on 10,000 to 100,000 preference pairs. And GRPO takes the align model and produces a reasoning model trained on 10,000 to 100,000 problems with reward functions. Each phase is an order of magnitude smaller in data than the one before it. Key insights. Each phase has a single primary job. Pre-training instills language ability and world knowledge. SFT teaches the model to follow instructions. Alignment shapes behavior around human preferences and safety. GRPO develops the capacity for step-by-step reasoning. These aren't overlapping, they're additive. Each one builds on what came before without replacing it. The data scale drops dramatically at each stage. Pre-training needs trillions of tokens. SFT works with millions of examples. Alignment needs thousands of preference pairs. GRPO needs thousands of problems. This is why fine-tuning is accessible. You're working at the narrow, affordable end of the data pyramid, on top of a foundation that cost millions of dollars to build. When you're planning your own fine-tuning project, map your goal to the right phase. Want to add domain knowledge, medical literature, legal documents, proprietary documentation. That's continued pre-training. Want to teach a new task or response style. That's SFT, and it's the most common case. Want to improve safety or align outputs with user preferences. That's alignment with DPO. Want your model to reason through problems step by step. That's GRPO. Pick the right tool for what you're actually trying to achieve. One final point worth internalizing. Llama 3 didn't do SFT once and ship. The actual pipeline was base model, then SFT, then DPO, then SFT again, then DPO again. Multiple rounds, each one refining the previous result. Quality is iterative. Your first fine-tune is a starting point, not a final answer. Check your understanding. 5 questions to test your grasp of this material. First, what does the model actually learn during pre-training? The answer is language understanding and world knowledge. Grammar, facts, common sense, code patterns, basic reasoning, all acquired by predicting the next token on unstructured text. Second, what's the difference between a base model and an instruct model? A base model comes out of pre-training and can complete text but can't follow instructions. An instruct model comes out of SFT and can follow instructions, answer questions, and hold conversations. Third, what data format does alignment training use? Preference pairs, a prompt with a chosen response and a rejected response. Fourth, how does GRPO differ from SFT for teaching reasoning? SFT requires demonstrations of step-by-step thinking. GRPO only requires questions and a reward function. The model discovers reasoning strategies on its own. Fifth, does pre-training need more data than SFT? Yes. Trillions of tokens versus thousands to millions of examples. Not even close. Practical exercise. Identify the phase. 5 scenarios. Match each to its training phase. A model completes the capital of France is with Paris. That's pre-training. Factual knowledge absorbed from unstructured text like Wikipedia. A model responds to write me a haiku about computers with an actual haiku. That's SFT, because following a specific format instruction requires supervised fine-tuning. A model refuses to answer how do I hack a website? That's alignment, where safety behavior and refusal of harmful requests get trained in via DPO or PPO. A model shows step-by-step work when solving math problems. That's GRPO or SFT with reasoning demonstrations if you're providing explicit examples. And a model that understands medical terminology and anatomy. That's pre-training or continued pre-training on domain-specific text like medical papers and textbooks. Assignment. Plan your fine-tuning phase. Before moving on, take 5 minutes to apply this to your own project. Answer 4 questions. Which phase will you be doing? Continued pre-training, SFT, alignment, or GRPO? Why that phase? What specific capability are you adding? What will your training data actually look like, and how much do you need? For continued pre-training, plan for at least 100 million tokens. For SFT, somewhere between 100 and 10,000 examples depending on task complexity. For alignment, 50 to 5,000 preference pairs. For GRPO, 100 to 10,000 problems with defined reward functions. Writing down concrete answers to these questions now will save you a lot of confusion later when you're staring at a training script wondering what to feed it. Here's an example answer to make this concrete. The goal is a medical diagnosis assistant that outputs structured JSON based on patient symptoms. The right phase is SFT. This is a task teaching problem, not a knowledge problem. The training data consists of input-output pairs where the input is a description of patient symptoms and the output is a correctly formatted JSON diagnosis object. A reasonable target is at least 1000 examples, which gives the model enough variation to learn the output format reliably across different symptom presentations. That's the kind of specificity you want in your plan before you write a single line of training code. Key takeaways. 5 things to carry forward. Training is multi-phase. Pre-training, then SFT, then alignment, then optionally GRPO. Each phase adds a distinct capability. Knowledge, then instruction following, then safety and preference. Data requirements shrink at every stage from trillions of tokens down to thousands of examples. In practice, you'll spend most of your time doing SFT because it's the most versatile phase for custom use cases. And GRPO is genuinely cutting edge. If you have a domain with verifiable outputs, you can build a reasoning model without ever writing a single reasoning demonstration. Next lesson. Now that you understand the full training pipeline, the natural next question is, how do you actually fine-tune a 7 billion parameter model on consumer hardware without running out of memory? The answer is LoRa and QLoRa, and that's exactly what lesson 1.4 covers. If you want to go deeper on anything from this lesson, the Llama 3 paper has full details on their training data mixtures. The original RLHF paper, Learning to Summarize from Human Feedback, is the foundational reference. The DPO paper, Direct Preference Optimization, explains the math behind the simpler alignment approach, and Searching for Group Relative Policy Optimization will get you the GRPO paper. All worth reading when you're ready. Skip. This chart shows the data scale at each training phase, and the numbers are worth sitting with for a moment. Pre-training for a model like Llama consumed 15 trillion tokens. That's the entire foundation of language understanding and world knowledge. Supervised fine-tuning used around 1 billion tokens to teach instruction following behavior. RLHF preference data came in at roughly 1 million tokens, and your fine-tune approximately 50,000 tokens. That last bar is the one that matters for you. It means that with a well-curated dataset of a few thousand examples, you can meaningfully change how a model behaves, because you're building on 15 trillion tokens of foundation that someone else already paid for. This chart maps each training phase to the capabilities it develops across 5 dimensions: language fluency, world knowledge, instruction following, safety and alignment, and reasoning. Pre-training dominates on language fluency and world knowledge. Those 2 dimensions are almost entirely built in that first phase. SFD is where instruction following ability jumps dramatically. The alignment phases, RLHF and DPO, are primarily responsible for the safety and alignment dimension, and your fine-tune sits at the top, adding targeted capability in whatever specific domain or task you're building for. The key insight from this chart: by the time you start fine-tuning, the hard work on language and knowledge is already done. You're customizing a highly capable foundation, not building from scratch. This diagram shows a single transformer block, the fundamental computational unit that stacks dozens of times inside a large language model. Input tokens enter at the bottom and get converted into embeddings with positional information, so the model knows both what each token is and where it sits in the sequence. Those embeddings flow into the multi-head self-attention mechanism, which is where the model learns which tokens are relevant to each other, the contextual relationships that make coherent language generation possible. The output gets added back to the input and normalized, then passes through a feed-forward network that captures more complex patterns. Another add and normalize step follows, and then this entire block repeats, sometimes dozens of times. Each layer refines the representation. Understanding this structure matters for fine-tuning because when you use LoRa, you'll be targeting specific layers within this architecture. Knowing what those layers do helps you make better decisions about where to apply your training. This diagram shows the alignment pipeline side by side for RLHF and DPO. Both start from the same place, an SFT model and human preference data. In RLHF, that preference data first trains a separate reward model, a neural network that learns to score outputs the way humans would. Then PPO optimization uses that reward model as a signal to update the SFT model, producing the aligned result. DPO cuts out the reward model entirely. It takes the preference pairs directly and optimizes the SFT model against them in a single training step. The aligned model you get at the end is comparable in quality, but the path is significantly simpler. For practical fine-tuning work, DPO is almost always the right choice. Fewer moving parts, more stable training, and no need to maintain a separate reward model. This diagram shows exactly how GRPO works mechanically. Start with a prompt, a question or problem. The model generates a group of candidate responses, typically 8 at once. Each response gets scored by your reward function, which checks correctness, formatting, and the presence of reasoning. Then the algorithm computes the advantage of each response, how much better or worse it performed relative to the group average. Responses that scored above average get reinforced. Responses that scored below average get penalized. The model updates its weights accordingly, and the process repeats. Over many iterations, the model learns that responses with explicit reasoning consistently score higher than responses without it, so it learns to reason. The group comparison is what makes this computationally tractable. By scoring responses relative to each other rather than against an absolute standard, GRPO avoids needing a separate reward model while still producing meaningful training signal.